Welcome back to Chapter 8. This is Lecture 6 from Chapter 8. We're continuing on our tour of the periodic table. So we've made it through the alkali metals, the alkali earth metals, the transition metals. So hopefully you found a couple of them in here that sound familiar. Titanium. This is often used in things like surgical implants. You've got tungsten. You may have heard of that. That's a property metal to put into some high stress materials. We've got chromium, molybdenum. Those are often put into different alloys. Iron, that's a common one for steel. Cobalt, we also use in a lot of different structural metals. Same with nickel. These guys are both common to use. And also remember, cobalt is magnetic, just like iron, which actually, if you think about it, makes sense since they're close on the periodic table. There's zinc, the one I was talking about before. You've got copper, silver, and gold. You'll see that mercury is here in the transition metals, even though it is liquid at room temperature, but it is part of the transition metals because it has properties in common with the other members here in its family. So we've now made it over to the right-hand side of the table, so we're going to pick up with 3A. So on the right-hand side of the table, I mentioned that the first couple of families on that side of the table have no common family names. So the only thing I'm going to point out here are some of the ones that you're familiar with. We saw already, let me flip back over. You've got things like carbon and nitrogen are in these families because we're looking at 3, 4, and 5. You got things like phosphorus. Aluminum is in this group. It is a metal. You'll see though it's not a traditional type metal like the transition metals. These guys over here that are in this kind of different color blue are considered metals. Sometimes they're called poor metals by some groups because they are in this different group. Leads over here as well. And tin, these guys aren't nearly as strong as the other guys in the transition metals. Think about it like aluminum. We can make it fairly strong, but it's lightweight and it takes a lot of the material to make it strong. Think about like an aluminum can. You can crush that pretty easily. Lead is pretty malleable. It's not a real structural type of metal. We've also got arsenic in these groups over here, along with the nitrogen and phosphorus. So the big thing to look at here is just the pattern that we've been seeing. So we saw with 1A, 1 outer electron, 2A, 2 outer electrons. So I'm hoping it's not a surprise that 3A has 3 outer electrons. So that means 4A, 4 outer electrons, 5A, 5 outer electrons. Hopefully you're starting to see a little bit of a pattern here. For the A families, their numbers actually match their numbers of their outer electrons in the outermost shell. So that means that we've now gotten to our next group that actually has a name. So 6A, which are the chalagens. These are what we call ore forming. Actually, chalagen in Greek means ore forming. So these guys have 6 outer electrons. I know, shock. So these are fairly reactive. So they have 6 outer electrons. We'll talk more, especially in the next chapter, about why having 6 outer electrons makes you very reactive. But they're kind of like the opposite of what we saw on the first 2 columns. So like the alkali metals and alkali earth metals are very active. Well, we've gotten to kind of their partners on the other side. So these guys are going to react easily. So the one that you can see here is sulfur. Oops, sorry. I want to just pop over to the table real quick. Oxygen is here. If you think about it, a lot of compounds contain oxygen. Water, carbon dioxide, nitrogen oxide, sulfur dioxide. Those are the ones I can think of off the top of my head. But a lot of metals actually contain oxygen. So ferric oxide, that's rust. Zinc oxide, that is the compound that you put on your nose as sunblock. So these guys are really reactive. And so they will generally not be by themselves. The one exception to that would be oxygen and sulfur, but they react with themselves to make pure compounds. So they're not found as single atoms. All right, we keep going. Our next group is 7A, and that's the halogens. Halogen is Greek again, in this case for salt forming, because the members of this group are going to bind with other elements to make salts. Mainly the members of this group are going to bind with members from the alkali metals, sometimes the alkali earth metals, in order to make salts. So the one that you know the best from this group probably is chlorine. Because it binds with sodium to make sodium chloride. And this group, I know it's a surprise. At this point, it's going to have 7 outer electrons in its outermost shell. These are highly reactive. So when these guys are around, they will very much want to react with other elements when they run into ones that they can react with. Chlorine is this one right here. It's this yellow gas in this bubble. This is a pretty nasty gas. This has been used in different types of war actions because it actually will burn and kill you because it burns your lungs. The next one we have over here, because like I said, from salts, sodium chloride, but you actually might know this guy. This is bromine. So you might see bromine in, for example, some disinfectants. And then the guy over here, the purple, is another one you may know from salts because it's one that we enrich salt with. This is iodine. So it will be bound usually to something like potassium to make potassium iodide. And so we actually put that in our salt. If you've seen iodized salt, that's what it means. It's got iodine compounds in it because we need iodine in part of our diet as one of the elements for our different body chemistry reactions. The last group, group 8, that's the far right-hand column. These are the noble gases. They have a full outer orbital, meaning they do not have any missing electrons in that outermost shell. So their outermost shell is completely full. So they are completely cool to sit by themselves. They are going to be colorless and odorless, unlike the other gases that you find in the other parts of the periodic table. Some of the other ones are colorless and odorless, but these are all colorless and odorless. It's one of the features of the group. And these guys are unreactive gases. They don't tend to combine with other elements. We can force them to combine with other elements under certain conditions, but on their own, they're going to hang out by themselves, and they can hang out by themselves as individual atoms. And it's because of this full outer orbital. They don't need to borrow or steal electrons, as we'll see in the next chapter. And so this is part of why they have this name. The noble gases is the name that they were given because the nobility in the past was very standoffish and didn't combine with the lower classes. And so that was kind of the idea of giving them the name noble gases, because these elements stand alone by themselves. They don't combine with other elements. You can see the different ones here. So we've got helium, neon, argon, krypton, xenon. These are the main ones that you'd come across. And you may recognize neon and look at these and go, well, those are all neon signs. Well, the only neon sign that you see that is actually going to contain neon is the one that looks orange like this. The other colors are either going to be individual noble gases or combinations of those gases and others. So that's how we get those different colors for our neon signs. All right, one last section of the table to look at, and that is what we call the rare earth elements. These are all very reactive elements with very similar chemical properties. The problem is that these were actually not recognized as elements until much later than the others on the table. So a lot of the rest of the table was filled in, fairly early, but these guys were recognized much later, late 1700s to early 1800s. So the big problem here is because they're so reactive and they look so similar to each other, it took us a while to start isolating them. The thing is, their name is not correct. They're not actually rare. We thought they were rare because of our difficulty in isolating them, but they're actually more abundant than most of our metals that we are using on a daily basis. So they're more abundant than gold, silver, mercury, the metals that we're used to hearing about and talking about. The rarest rare earth element, which is thulium, is twice as abundant as silver. And if you think about it, we're not really talking about a shortage of silver. So that gives you an idea of how not rare the rare earth elements are. And they're not earth elements. I mentioned earlier that earth generally is meant as non-metal because it doesn't react in fire. The thing is that the rare earth elements are actually metals, but they're bound in mineral form. So they are bound because they're so reactive, they're bound into minerals, and that's why they don't act like metals. So let's take a look at who these are. They are the lowest rows in the table. So there are those two low rows on our table. It's the pink and the purple, the lanthanides and the actinides. And these guys have been pulled out because they have these different properties. So let's look at these two groups in a little more detail like we did with the others. So the top row are the lanthanides. So this is the 6th period of rare earth elements. So if they were in where they belonged, they'd be in that 6th row. They are, like I said, they're similar to each other. They are similar to each other in physical characteristics. So you can look up here. I mean, it's nearly impossible to tell these 4 metals apart. They're all kind of the same color. They take very similar shapes. In fact, their chemical characteristics are even very similar to each other, which is why they actually act the same when they are in any sort of mineral situation. In fact, they are usually found together and can be very difficult to purify, which it makes them fairly expensive because of the time and effort it takes to get them out. Even though that they're not rare, it's just the process that it takes to get them that makes them expensive. The thing is that we use them all over the place. They are found in your LED screens. We use them in fiber optics, laser crystals, magnets. So you guys actually used some of the lanthanides when we did our electricity lab, the neodymium magnets, those super strong magnets that were like in the containers and so forth. Motors, ceramic superconductors, even jet parts, jet engine parts are now built out of lanthanides because of their unique properties. The actinides are the lower row that are underneath the lanthanides. So this is the 7th period rare elements. These also have similar properties to each other and are difficult to purify if they are found together. So the question is, why would we want to? Why would we want to get these elements? Well, if you take a look at the 4 that are up here, actinium, thorium, proactinium, and uranium. Well, some of those may sound familiar. There are 3 elements in the actinides that are pretty useful for us. The nuclear elements of uranium, thorium, and polonium. Plutonium. Now, you might notice that plutonium isn't up here. That's because plutonium is a man-made element. Actinides heavier than uranium are only created in labs. So anything higher than 92 on the periodic table in this row is man-made. So if we take a look at that periodic table again, so here you've got those 4 that I just showed you. Anything above that, neptunium, plutonium, and on all of these ones that are in these kind of whiteout kind of letters, those are all man-made. So you can actually see there's a couple of man-made ones in other parts of the table too. That's because like tectinium actually reacts pretty quickly once it's formed to turn into other elements. All right, so I'm going to stop here and pick up with the last section of this lecture in our next video.